Hello. Today I want to talk about sigmatropic rearrangements and in particular hydride shifts. So this is a process that we talk about in intraorganic when we do sort of the hydride shifts from one neighboring carbon to another. But this is a process where we're having a hydrogen shift over more atoms, 3 atoms, 5 atoms, something like that. So I have an example up here that I want to start with. And so this is a situation where we have 5 carbons and we have a hydrogen shifting from one end to the other, right? And so first we need to make sure we know how to number this correctly, right? And so when we think about numbering in sigmatropic rearrangements, as we've talked about before, you find the bond that is migrating, the sigma bond that's migrating, you number around the pi system and you figure out where the bond is that comes together. So the bond that's breaking in this case is going to be this CH bond. So again, we'll number that a 1 on either end of that bond. And since the hydrogen is moving, that just stays as 1. We don't go any more numbers there. And then we just number around the carbon pi system. And so we note that we're now going to form a bond here, right? So if we draw the curved arrows for this, this is the bond we're going to form. And the curved arrows look like that. And so we're forming a bond between the 1 position, the hydrogen, and the 5th carbon. So this we would label as a 1,5 hydride shift. Okay, so it's a 1,5 sigmatropic rearrangement. Interestingly, we don't ever see this shift. If you do the numbering for this, this would result from a 1,3 shift. We only see the 1,5 shift, right? And one important question before we sort of figure out why 1,5 and not 1,3 is just to understand, how do we even know this is happening, right? These things, just flip it over, it's the same thing. The way that we know this is happening is if you deuterate one of these things, you can see deuterium actually move around the molecule, right? So one thing we can do to visualize this is deuterate the methyl group. Heat that molecule up, and you'll see that the deuterium actually moves, and you can see this very easily by NMR, so that we're going to make that bond and do the exact same process that we've illustrated above. And you can see that the deuterium moves from one methyl group to the other, and you get scrambling of the deuterium, right? So that is the way that we tell this is going on. And again, we do not see evidence of the 1,3 shift. Sorry, make that a deuterium. We don't see the deuterium at the 3 position. Okay, so we know the 1,5 is happening, the 1,3 is not happening, right? The interesting thing is if you take this same material and you treat it with light, you do get the 1,3, right? So let's erase this where it says not. We get the 1,5 shift thermally, right? So 1,5 is a thermal process, and the 1,3 is a photochemical process, right? Just like we've seen with electrocyclic reactions and cycloadditions, if you heat it or if you shine light on it, you get different processes to occur. That happens here. And again, how do we explain those other things? We explain those other things by looking at the molecular orbital diagram, right? And so let's just think first about what the transition states look like for these, and then we'll see what molecular orbital diagrams we need to draw. So if we think about the transition state for the 1,5, right, we could draw this. So draw the carbon framework, right? And then we have a hydrogen or a deuterium, and I'll just put hydrogen, right? We'll sort of circle it since hydrogen is going to be an s orbital, and that is migrating across that 5 carbon system. And so the way that we think about this and the way that we're going to be able to look at the molecular orbital picture is if we imagine an H radical migrating across a pentyl radical. All right, so when we look at the molecular orbital picture for that, we're going to have to draw out the 5-carbon pentyl system and then see what the molecular orbitals look like. For that, for the 1,3 shift, all right, what does that transition state look like? Again, we'll just use H. So we have an H radical migrating across an allyl system. So for us to draw out what's happening, we have to draw out the molecular orbital picture for a pentyl system and for an allyl system, right? And so while I erase this, that'll give you time to draw out what those 5 and 3 atom pi systems look like. All right, so the easier one is going to be the allyl system. So let's start with that. All right, we've drawn out the allyl system before. And if we think about what the allyl radical looks like, we're going to have psi1, psi2, psi3. And again, we have 3 pi molecular orbitals to worry about. We have 3 electrons. So we think about where those electrons are. They're going to be 2 in psi1, 1 in psi2. So if we shine light on that, we're going to promote the electron from 2 to 3. Right, and so when we think about what's going on here, under photochemical conditions in the excited state, our highest occupied molecular orbital is going to be psi3. And that's where the chemistry is going to occur. So in sigmatropic rearrangements, the chemistry occurs out of the HOMO, just like when we think about electrocyclic reactions. Right? So if we think about what psi3 looks like, again, when you're in the highest molecular orbital, that's actually a pretty easy one to draw because you have overlap nowhere. So we have 2 nodes, we have no overlap. And so if we think about what this looks like in terms of a hydrogen atom migrating, right, we're going to have a situation like this where we have H migrating across that system, and you can see that the hydrogen can migrate from the bottom face to the bottom face, right? And so the terminology that we've been using for this is we would say this is a suprafacial shift. Right, again, much like a syn addition to an alkene, we're forming and breaking bonds on the same face. Okay, so superfacial shift. Superfacial shift is possible, right? That's something that will occur and that will be possible. And again, only in the excited state, so it has to be excited. So now let's look at the pentyl radical. So for the pentyl radical, we're going to have 5 molecular orbitals. And again, we're going to have 5 pi electrons, right? 2 from the pi bond, 1 from the radical. So we have psi3. Since this is going to be a ground state reaction, psi3 is going to be the HOMO. Right? And so now we have to figure out what psi3 looks like, which is not always the easiest thing in an odd number system. So if we think about that, we're going to have 2 nodes. And with an odd number system, the 2 nodes are going to go through 2 atoms, right? So what this will look like is this, where we have nodes going through 2 of the atoms. And so we can fill in the signs of the orbitals, and that's going to be our HOMO, all right? So if we draw out what this is going to look like, all right, we're going to have, try to draw this correctly. And again, we have our two nodes there. We have a situation that looks like that, so that's psi 3. And again, if we put the hydrogen here, we can see the bonds we're forming are both to the bottom face. So this is also a suprafacial shift, right? Just like we drew above for the allyl system, right? If we looked at, so again, this is the 1,5. If we looked at the 1,3 for the pentyl radical, right? So draw the same molecular orbital. So if we had the H shifting in a 1,3 fashion, what sort of process would that be? We can see that the H would be shifting in an anterofacial fashion. Again, like an anti-addition to an alkene, we have the H forming a bond or breaking the bond from an orbital on the bottom and then moving to an orbital on the top. So this would be an anterofacial. And for small rings like this, again, this would be 3 carbons and a hydrogen, so a 4-atom transition state. Anterofacial shifts just don't happen, right? So I think this is important to note. These anterofacial shifts are not possible in transition states of 6 or smaller. And it is possible, and there definitely aren't many examples of these anterofacial shifts, but they have to be over larger systems, right? When you get to 7 atoms, things like that, then you can have these anterofacial shifts, okay? So when we're thinking about what is possible, we can draw out the Woodward-Hoffmann rules for sigmatropic rearrangements, all right? So let me just erase this, and then we'll draw out the rules, and then we'll be all set with the hydride shifts. Right, and like we have done for electrocyclic reactions and cycloadditions, we can draw out a chart that very quickly tells us what is possible based on the number of electrons involved. All right, so if we have 4n plus 2 or 4n pi electrons, 4n plus 2 thermal is going to be suprafacial. That's what we just saw for the 1,5 hydride shift. So that means that one's going to be anterofacial, anterofacial, and suprafacial for 4n photochemical. That's what we just saw with the 1,3 hydride shift. And also, if we think about the other sigmatropic rearrangements that we've seen, think about the Cope and the Claisen 3,3 sigmatropic rearrangements. Those are 4n plus 2, suprafacial, thermal, right? And that's often where we're going to operate. But this will help us when we're looking at hydride shifts we might not have talked about today, whether they're going to be suprafacial or anterofacial, and then we can figure out the consequences from there. All right, so hopefully this helps as you think about hydride shifts that you might see in your homework or in upcoming assignments.